Welcome to part 2 of calculating the capacitance for a cylindrical capacitor. Now over here, what I'm going to show you is all the work that we did in part 1 was to just figure out an expression for the electric field, which is not constant between these two. And now we're at the point where we can figure out the expression for V as a function of R, so that we can ultimately do step 3. So let's take a look at that. Now the electric field the electric potential at infinity, okay, is going to be 0. Now there are some considerations to take here that we are going to simplify the situation a little bit, and so I'm not going to go into them in great detail here, but sometimes you pick a different point for the potential to be 0, but for right now, let's just say that the potential at infinity is going to be 0. Now if there's no electric field outside of B, then there can't be a potential difference outside of B. And if the electric potential at infinity is 0, then the electric potential at B needs to technically be 0, because there can't be a difference, right? Delta V has to be a difference of 0. And so we should have a function that has just 0 across here from B to R. Now from 0 to A, again, we have no potential difference, but we know at A, that's the point of highest potential. So the difference, yes, between 0 and A still has to be equal to 0, but the potential at A or at 0 is not necessarily 0, it just has to be a difference of 0. So what we're going to say is the potential at 0 is equal to the potential at A, and it's some non-zero value, and I'm going to go ahead and just pick one. Okay, so maybe we'll make it right here. Now, the function that we put in for E, okay, all the way from up here, that's going to show us what function we will have from A to B. Now we know that the potential is going to drop from the positive to the negative, right, as we look at this situation here. So that's what we're going to kind of keep in mind to check ourselves when we do this. So what I'm going to do here is just do a very rough, quick sketch of my cylinder, okay, and my inner cylinder. And I'm going to say I'm going to integrate from the outer shell, which is B, to the inner shell, which is A. Okay, and when I do that, if I think about my expressions here, I'm going to go from B, okay, so I'm figuring out the delta V from B to A, and that's going to be my integral, right, from B to A, E dot dr, and it's going to be negative because the electric field line points outwards, right, but my path over which I'm integrating is going inwards, and so the negative comes into play over there. Now I'm going to go ahead and substitute in my expression for, let me get some space over here. I'm going to go ahead and substitute my expression for E into this function over here. Okay, so I'm going to say it equals negative integral from B to A of lambda over 2 pi epsilon naught. Okay, so that's all the little constants, right? And now R is the actual variable, the independent variable, and so I'm going to put it here on its own. dr is the variable of integration right here. Okay, so I have dr over r. Now what I'm going to do is pull out all my constants, so I have negative lambda over 2 pi epsilon naught integrated from B to A of dr over r. Okay, now we know this one, the integral of 1 over r with respect to r, or 1 over x with respect to x, is the natural log of x, right? So what's going to happen here is I have negative lambda over 2 pi epsilon naught, and then this is going to be natural log of r from B to A. Alright, now I'm going to put in my values here, so I'm going to have negative lambda over 2 pi epsilon naught times the natural log of A minus the natural log of B. Okay, And what I'm going to do is I want to get rid of this negative sign here just for the expression so that it's a little bit less cumbersome, right? So if I multiply that in, these will just switch direction, right? Because this will become positive, that will become negative. So I can write it as natural log of b minus natural log of a. So that's going to be lambda over 2 pi epsilon naught times natural log of b minus natural log of a. And one of my log identities is that the natural log of something minus something is natural log of that over this. So I'm going to go lambda over 2 pi epsilon naught times the natural log of b over a. And this is the expression for the voltage. So this is the expression between the a and b, right, where b is at 0. So if I do some sort of natural log function here, look at something kind of like that. They look very similar, right, from just the perspective that I'm drawing them at. Okay, we're almost ready for step 3, which is to actually figure out the capacitance, which is what this whole circus is all about. So let's go ahead and do that. Okay, so we're trying to figure out this capacitance. We know it's Q over V, and we just found our expression for V. So what I'm going to do here is I'm going to plug everything in. Actually, I'll do it up here. So we have Q over, okay, all of this, lambda over 2 pi epsilon naught times natural log of B over A. All right, so technically what's got to happen here is this is a complex fraction, and so I'm going to multiply by the reciprocal. Okay, so I'll end up with Q times 2 pi epsilon naught over lambda times the natural log of B over A. Now this lambda over here, so I'll write this out, is, remember, Q over L. And so when I plug this in, I'm going to plug it in instead of a complex fraction as L over Q, right? So I'll have Q times 2 pi epsilon naught times L over Q, that's the lambda, L over Q, times the natural log of B over A. Even the simplification's annoying. It's taking forever. Okay, so now we need to get rid of the Q. We can factor that out, which does actually make sense for the capacitance. We'll talk about that in a second. Where we have here now an expression 2 pi epsilon naught times L over the natural log of B over A. And that's actually the expression for a cylindrical capacitor. And if you look at it, right, compare it to the expression for the parallel plate capacitor, it's all about geometry. All about geometry. Everything here is about geometry, and so it's a good thing that the Q canceled out. Because that, remember, we showed from the lab results that Q did not have an effect on the capacitance. V did not have a direct effect on the capacitance. Only the geometry did. And so here we see this natural log of B over A. This is not some fancy math term. This is just the outer and the inner radii. This is the length of the capacitor, right, which would determine how much charge it could hold. The longer it is, the more charge it could hold. And then obviously we have some constants. So this, in the end, is the answer to the whole video. But just remember, the main point here is to remember that we're trying to say if the capacitance is Q over V and V is E dot dr, it makes sense that I have to go from figuring out the electric field in the capacitor to figuring out the voltage across the capacitor, and then I can know the capacitance. So this is a great summary process of making sure that you understand all the electrostatics that has happened up to this point. In subsequent videos, we'll take a look at a spherical capacitor, all right, and do a very similar situation. It's not as long once we've done it one time, and then we'll take a look at the energy inside the capacitor.